Yep, that worked. Thank you.
Good.
Yeah, so he was just making a couple last minute adjustments to his slides. So.
Very understandable.
Yeah, I mentioned to him that probably not everyone is that familiar with Fourier transforms. So.
No, I was very surprised that in my E&M class, yeah, people were really rather at sea with respect to Fourier transforms, and I thought that their regular math sequence would definitely. I think they went past. I mean, they covered it, whatever that means.
I'm not sure they do. So in differential equations, I think they only deal with Laplace transforms.
Mm-hmm. But not Fourier, of all things.
I mean, my daughter took a differential equation class this summer, and it was all Laplace transforms, nothing with Fourier transform in the textbook even.
Really? Well, that's too bad.
So I don't know where the Fourier transforms are actually seen. Probably the first physics course that either quantum mechanics or E&M.
Well, I don't remember having this much trouble before. But there's Simon.
Hi.
Showed up. Okay. We're having well, it just cleared up a little bit, but we had this rainstorm and a half. How's your weather?
Oh, actually, it's fantastic here. You know, it has been a little bit warmer than usual, but we welcome that. This week it has been hovering around 70, so that's, you know, it's a little bit warmer. So we take advantage of it by taking long walks, you know, outside.
Well, last night my husband said it's 69 degrees, and I wondered. I thought, wow, something's wrong in this erratic Michigan weather.
So it sounds like you have the same kind of weather that we have here. Then it's.
Where are you right now?
I'm in Maryland, just outside of Washington, D.C. Yeah.
I used to live there.
Oh, okay.
But that was a long time ago.
Okay.
Yeah, my sister went to Johns Hopkins, so that's where you are, right? You're
yeah,
at
that's right. Yeah.
Applied Physics Lab.
Yeah. So the main campus is in Baltimore, but the Applied Physics Lab is in Laurel, which is halfway between Washington D.C. and Baltimore. But I live closer to Washington D.C. because my wife works closer to Washington D.C. Yeah.
Mm-hmm.
So I think I want to turn off the light in this room because it's too bright. Just give me a second.
I had to do that to one of my lamps. I had to turn it down.
Yeah. So while we are waiting for people to show up, can I see if I can
please
share my screen and and see if there's any problem with the connection?
Yeah, that's good.
All right. So I'm going to share my screen now and see what.
Oh, wait a minute. I have to give you co-host permissions. Okay, that'll be better. Okay, let's see. Okay, it's showing.
Can you see my screen?
All yes, right. We can.
And it should look very big now on your screen. Okay.
Right. Mm-hmm.
All right. So I can stop for now, just because if I share my screen, then I cannot see the participants.
So do you consider, how much of your work do you consider to be nonlinear? All of it, half of it, a little bit of it?
It depends on the project, but yeah, I would say maybe half of it what will be nonlinear using information theory. So this is something that I have been doing a lot recently. In the last 5 years or so, I collaborate with Professor Jay Johnson there, and but before that, I have done a lot of other things. But information theory is something that I have been passionate about in the last 5 years, I would say.
Oh, nice. Well, we're
Yeah.
going to really appreciate your talk today.
Okay, thank you. Thank you for inviting me here.
Yeah, I don't know. Have we met in person or not?
I'm not sure. I visited the campus a couple years ago, I think, and I would like to come back again because I collaborate closely with Jay Johnson. So I hope that I will be able to see you in person soon when.
Well, we have a desk with that we reserved for you, so.
Yeah, right. Yeah, I would like very much to see the office. I enjoy it when I was there last time. It's a nice campus, and
Well, right now it's very dead. There's hardly, it's just so quiet and there's so little going on that's visible.
yeah, I can imagine. It's the same way at the Johns Hopkins University. It's quiet.
Very quiet.
It's awful.
Well, some things you can actually do better. Yeah, I mean, because you have these, you don't have as many distractions. On the other hand, it seems like everything you have to do a little bit differently, and that's distracting in itself.
Yeah, we do a lot of Zooms, and so I think that helps. But on the other hand, it can be very easy to get a Zoom fatigue. So
do they have studies these days for how does that happen? Why is it so bad?
Yeah, I don't know. I've heard different theories about it. Like it seems like some people get tired more easily because there is a delay between the voice, the sound from using computer, and that introduces some additional processing or stress, and also in a group meetings situation, it's hard to without seeing the body language, it's hard to know when the person is finished talking and now it's time to jump in, it's hard to gauge that.
Right. Now, my theory is it's that back and forth, that you do in person, and you can read each other.
Exactly.
The other
Yeah.
one is the narrow angle that we are focused on over long periods of time.
Right.
Whereas in a room, you can scan, the whole room.
Right.
And yes, you spend most of the time on somebody's face, but it's not all the time. Whereas here, it's all the time.
Right.
Yeah. Today's the 23rd. Today's Guillermo's.
Yes, today is the 23rd, and the day that we have Dr. Simon Wing joining us. And
5 years ago.
we have an open mic. Let's see if we can get those. Can I close those? Brendan, can you close the open mics? Maybe not.
I think it's been done.
Okay, good. Anyway, we were delighted coming to us from Maryland, and technically part of our department. And we're really happy that he is good friends with Jay Johnson, and together they do lots of mischief. And we're going to find out what it is that they've been talking about, and the things that we are very interested in. Many of us are interested in nonlinear processes, and so that we're really looking forward. I'll let Jay Johnson give a little bit of another angle by way of introduction.
All right. So Simon or Dr. Wing and I pretty much came into the field of space physics around the same time. So he got his degree at the University of Arizona, and after a short time, he was hired at the Applied Physics Laboratory at Johns Hopkins University, and very quickly got interested in research projects with a number of people there, and he. I remember meeting him at one of the space physics meetings, probably in the mid '90s or so, mid to late '90s, and we just developed a really good friendship. And whenever we go to the meetings, I remember we would sit and play chess together or something like that, and just we go for hikes and things like that. Sometimes we would go on a. I think we went once to Japan, and we went for an outing, an excursion up into a volcanic area, and just out of the discussions that we had, ended up getting a proposal funded based on those discussions. So anyway. Simon has been just a really good collaborator. He's an observer and does modeling of observations, and so we really developed a very good theory observation relationship or collaboration over the last 20 years or so. I think our first joint publication was in probably like 2005, and most of our papers since that time have been joint publications. Yeah, I'm sure that we've co-authored probably the order of 40 or 50 papers together. So anyway, Simon and I first became interested in information theory back in the early 2000s, and I got a project funded at the Princeton Plasma Physics Laboratory to collaborate with him on this, and through the years we've just developed more and more interest in applying information theory to different types of systems. And so I think Simon's actually going to talk about a number of different topics that we have applied it to. And so by the way, Simon's degree is from Eindhoven in physics, and so I just want to invite you to present your talk.
Okay, thank you very much. Can I share my screen? Okay, so can everybody see my my screen now? All right, so okay, so first I would like to thank Andrews University for inviting me to give this talk. I visited the campus a couple of years ago, and I thought that it is a nice campus, and I would like to come back again whenever it's possible. Okay, so I would like to also thank Jay Johnson, who, as he mentioned, has contributed significantly to the work that I will present today. So, all right, so this shows the outline of my talk. I will give a brief introduction to information theory, and then I will present three applications, one at Earth, one at Saturn, and one at the Sun. I'm not sure if we have time to look at the Sun, but we'll find out. And then I will end with a summary. Okay, so two variables, say an input and output variable, can be linearly correlated, in which case standard correlational analysis can characterize the relationship. And the standard correlational analysis here may include finding correlation coefficient and a line that best fit the distributions. But the two variables can be uncorrelated, where the distribution looks like a circle of dots. In a complex system, the two variables can be nonlinearly correlated or can have high order correlations, in which case the standard correlational analysis will be inadequate. And so here information theory can be helpful. The bottom plot here shows the radiation belt electron flux versus solar wind velocity, which shows that the solar wind radiation belt system is nonlinear, and we will talk about that later.
What's up?
Was there any question? All right, so I will now give my brief introduction to information theory. Say that, by the way, if there's any question, please jump in. I don't mind. So say that we have variable x and y. The entropy of x is defined as the sum of the p log p, where p here is the probability distribution function, and entropy of y is given in a similar fashion. So entropy here gives a measure of the amount of information in a variable or in a set. In some literatures, different authors would use different descriptions. Some people would say the entropy gives a measure of uncertainty or a disorder, but they are all related. So this slide here gives some gives a highlight of the concept of entropy. Say that we have 3 buckets. In the first bucket, we have 4 red balls. In the second bucket, we have 3 red balls and 1 green ball. And then in the third bucket, we have two of each. So in the first bucket, we can have only 1 permutation of the balls, and so we can have 1 state. In the second bucket, we have 4 states, and in the third bucket, we have 6 states. So we can say that in the first bucket, the entropy is low. The second bucket, the entropy is medium, and then in the third bucket, the entropy is high. Another way to look at it, which is probably more closer to the concept of entropy as we calculate it using the equation that I showed earlier. In the first bucket, we need we only need 1 bit to record the number of states. In the second bucket, we need two bits, and then in the third bucket, we need almost 3 bits. All right, so now that we have some idea what entropy means, we can move on to the mutual information. Mutual information of x and y is just the entropy of x plus entropy of y minus the joint entropy of x and y, where the joint entropy is defined in the similar fashion. So mutual information, MI, is useful to identify nonlinear dependence between 2 variables. So pictorially, if entropy of x is blue, the blue circle, and entropy of y is red, the mutual information of x and y is this intersection region. So mutual information of x and y gives a measure of the information that x and y share. If x and y are independent of each other, then the mutual information of x and y is 0. So mutual information calculates the probability of knowing the y value when the x value is given. So here is an example that hopefully illustrates the concept. Say that we have coin flips. 50% of them are heads and 50% are tails. But we have 3 scenarios. In the first scenario, it's random. So if we knew the last coin flip, that would not give us any information about the next coin flip. And so the mutual information is almost 0. In the second scenario, if we knew the last coin flip, they would give us some information about the next coin flip. In fact, we would know what the next coin flip, except at the boundary here, and we have two boundaries. So the mutual information is high, it's about 0.82. And then in the third scenario, we have alternating head and tail. So if we knew the last coin flip, we would definitely know what the next coin flip would be. So the mutual information here is the highest, it's 1. So it's the same distributions, but different mutual information depending on the scenarios. All right, so here we compare and contrast the mutual information with correlations, like Pearson and Spearman correlations. So the distributions in the top panel have high correlations, both Pearson and Spearman correlations, and the mutual information is also high, except for the panel in the middle, where both correlations are 0 and the mutual information is also 0. In contrast, the distributions at the bottom panels show correlations are nearly 0, but the mutual information is non-zero, and that's because the distributions at the bottom panels are nonlinear, and the correlations cannot capture these nonlinear relationships. All right, so we move on to the conditional mutual information, CMI. CMI of X and Y given Z determines the mutual information between X and Y given that Z is unknown. So pictorially, if blue is the entropy of X, red is the entropy of Y, and green is the entropy of Z, CMI of X and Y given Z is this small region here. So if Z is random, then CMI of X and Y given Z is just simply the mutual information of X and Y. So I will use this quite a bit when I discuss the radiation belt. So if X or Y is known based on Z, then CMI of X and Y given Z is 0. All right, so now I move on to the third concept in the information theory, transfer entropy. A common method to establish causal relationships between two time series, X and Y, is to use a time-shifted correlation function. However, the results may not be clear if X and Y have multiple peaks. So say that we have X and Y as shown right here as a blue and red curves. They are both sinusoidal functions. It's possible that X can cause Y with a small time delay, but it's also possible that Y can cause X with a longer time delay. And one can find these time delays using time-shifted correlations, such as done right here on the right panel. The blue curve here is the correlation of X of t with Y of t plus tau. And the red curve is correlation of X of t plus tau with Y of t. But the peak on the blue curve doesn't necessarily mean that X causes Y. And conversely, the peak on the red curve doesn't necessarily mean Y causes X. So a better alternative is to use transfer entropy, which is shown right here. So transfer entropy TE of X to Y gives a measure of information transfer from X to Y, given that all the past values of Y are known. So if there is no information flow from X to Y, then TE of X to Y is 0. Unlike correlation, TE, which is symmetrical, TE of X to Y usually is not the same as TE of Y to X. So some studies have used transfer entropy to determine causality. Granger proposed some time ago causality principles. The cause has to occur prior to its effect. And the cause has unique information about the future values of its effect. So we can rephrase this in the time series analysis. X Granger causes Y if, in an appropriate statistical sense, X assists in predicting the future of Y beyond the degree to which Y already predicts its own value. So this is what transfer entropy aims to do. Granger also proposed a mechanism or a formalism to determine Granger causality. So transfer entropy can also do the same, except that the transfer entropy can take into account the nonlinearities in the system, whereas Granger causality only applies to a linear system. So Granger causality is pragmatic, well-defined, and has delivered many insights into the functional connectivity of systems in a variety of fields. All right, so using the same example that I showed earlier, if we know all the past values of y, that alone should be sufficient to predict the future value of y, because the y is perfectly sinusoidal, and so knowing x would provide little or no additional information, and therefore TE of x to y is 0, and for the same reason TE of y to x is 0. All right, so any questions on that? All right, so I'll just move on to the application, radiation belt dynamics. So unlike the Earth, Mars looks barren and has a thin atmosphere. And this can be attributed to the magnetic field. The Earth has strong magnetic field, whereas Mars has weak or no magnetic field or no significant magnetic field. But it is believed a long time ago, early Mars had a magnetic field and atmosphere. However, the dynamo stopped and the magnetic field weakened. And over time, the solar wind strips away whatever atmosphere that Mars had. So this shows the simulation of solar wind stripping away the atmosphere from Mars. So the solar wind is shown by these little white particles streaking from left to right. The sun is on the left, and now you can see the atmosphere gets stripped away by the solar wind. All right, so without the atmosphere, then there will be no water cycle. The water cycle here refers to this cycle of water evaporations, condensation, and then precipitation, which lives on Earth very much depend on. So at Earth, we are lucky. We have the magnetic field, which shields us from the solar wind. So this white contour here shows the streamlines of the solar wind, which the sun is on the left. So we can see that the solar wind comes streaming down towards the Earth and then gets deflected by the magnetic field. And this boundary here is the magnetopause, which separates the Earth's magnetosphere and from the solar wind. However, this magnetic shielding is not perfect. The solar wind, a small number of solar wind small fraction of solar wind can enter the magnetosphere from the flanks right here, or from what we call the cusp, from the top here. And the radiation belt, which is the topic, or the first topic of the application, is this pink region, which is about 10,000 kilometer in altitude, all the way to about 60,000 kilometer. So this is the region where a lot of the energetic electrons and ions are trapped. So this shows animation of one way for the solar wind to enter the magnetosphere is through reconnections. So the solar wind comes from the left to right, and then there is a reconnection which opens the magnetic field lines. and the solar wind blow the magnetic field line to the night side where they reconnect again, and the reconnection causes a substorm which energize the particles, the electrons and ions that follow the magnetic field all the way down to the ionosphere, leading to aurora emissions. So aurora is seen as a good effect of the solar wind magnetosphere interactions. Solar wind can be seen, observed from the space, from satellites, or from the ground. So the top panel here shows a movie of the aurora seen from space, probably from space stations. And the bottom here is the movie of aurora taken from the ground. I believe it's from Scotland. And the aurora actually appears, if you look at it from space, actually it looks like an oval because these regions here are the footprints of the magnetic fields that go to the magnetosphere, and the particles follow the magnetic field down to the ionosphere. And you can see the brightest region here is on the night side because that's where the energization occur. Okay, so that's a good effect of solar wind magnetosphere interactions, but these interactions also produce adverse effects. We call it space weather. Space weather can adversely affect a lot of our infrastructures. Some of them are shown here, such as it can affect the satellite communications. It can affect the astronaut health, airline passengers, telecommunication, cross-Atlantic telecommunication cables, and so on. So here I show that the space weather can affect our power grids. There is, during magnetic storms or substorms, the aurora electrojet, which is a current that flows in the ionosphere, get enhanced, and which can then induce currents in the electric cables. And there is one infamous event on March 13, 1989, in which almost the entire eastern half of Canada was blacked out because transformers get blown out by the magnetic storms. The space weather can also affect the airline travels. If you fly from North America to East Asia, say from Chicago to Beijing, Shanghai, Tokyo, the path will likely go through the polar region. But during magnetic storms, the polar region can be adversely affected by the enhanced energetic electrons and ions. And so FAA would require the flight to be rerouted to lower latitude, such as this event in January 2005, at a cost of about $250K in 2005. And I think today the cost will be close to $1 million because of the higher fuel costs and the crew overtime pay. So usually the airlines like United Airlines has drawn several paths from say Chicago to Hong Kong in this case. Depending on the magnetic conditions, they may choose one of these 4 paths. Okay, so this movie here shows just how busy these polar routes for the airplane travels globally. You can see these little dots here are airplanes flying, on Earth, and you can see that at night many flights from the U.S. And Canada would travel at high latitude to Europe, and then also from Asia, East Asia would travel at high latitude near the polar region to reach Europe. And so all these flights could be affected by space weather. All right, this is the Washington Post views of the space weather. They had a huge article on space weather several years ago. All right, so radiation belts are highly variable, and to a large extent, solar wind controls the radiation belt variability. But it's not clear which solar wind parameter plays the most dominant role. In geosynchronous satellites, which geosynchronous orbit is a very popular place to park the satellites because very little, because the orbit will be stable there, there's so little fuel will be needed. But unfortunately, geosynchronous orbit is inside the radiation belt. And over the years, many satellites have been terminated due to the radiation belt electrons. So this plot shows the radiation belt electron flux versus solar wind velocity, showing that the solar wind radiation belt system is nonlinear. So here I show plots of the radiation belt electron, radiation belt electron flux versus solar wind velocity with 0-day delay, 1, 2, and 7-day delays. The best correlation can be seen with a 2 days delay. That is the radiation belt electron flux, JE, of t plus 2 days with solar wind velocity of t. Well, it's hard to see the best correlation from these scatter plots, so more analysis is needed. So here on the right, I show the correlation of JE of t plus tau with solar wind velocity of t. And it shows that the best correlation is found at tau equals 2 days. But because the system is nonlinear, correlational analysis may be inadequate. So the bottom panel here shows the mutual information and the transfer entropy from solar wind velocity to JE. And it shows that the transfer of information from solar wind velocity to radiation belt JE peaks at tau equals 2 days. We can do the same analysis with the solar wind density. Solar wind density anti-correlates with radiation belt JE. And the anti-correlation has a minimum at tau equals 1 day. And the mutual information and transfer entropy analysis show that transfer of information from solar wind density to JE peaks at tau equals 1 day. But what is interesting is that the solar wind density anti-correlates with solar wind velocity, such as shown right here. And the transfer of information from solar wind velocity to solar wind density peaks at tau equals 1 day. So here's a summary of the observations. Solar wind velocity correlates with radiation belt electron flux, but solar wind density anti-correlates with the radiation belt electron flux. However, solar wind velocity anti-correlates with solar wind density. So given this solar wind property, if panel 1 is true, could panel 2 just be a coincidence? Conversely, given this solar wind property, if panel 2 is true, could panel 1 just be coincidence? Or is it possible that solar wind velocity and solar wind density each can exert influence on the radiation belt? So this problem can be reduced to a simple input and output problem. So the magnetosphere is the system, and it inputs many parameters, but here we just focus on solar wind velocity and density, and it outputs a radiation belt electron flux. So when solar wind velocity increase, radiation belt electron flux would also increase. When solar wind velocity decreases, radiation belt electron flux would increase. But solar wind velocity anti-correlates with solar wind density. So if we see an increase in radiation belt electron flux, is that because solar wind velocity increases or solar wind density decreases, or maybe both of these can cause the electron flux to increase? How can we tell? So in this study, then we use the conditional mutual information, which I discussed earlier. So the top panel here shows the CMI of JE of T plus tau with solar wind density, given solar wind velocities. So we have removed the effect of solar wind velocity. And we can see that it peaks at tau equals 0 day, which can be compared with the mutual information and TE of solar wind density to JE, which peaks at tau equals 1 day. So removing the effect of solar wind density shifts the peak from 1 day to 0 day. We can examine the effect of the solar wind velocity, which is done here on the top right panel, which shows the CMI of JE with solar wind velocity given solar wind density. And it shows a broad peak at tau equals 2 to 3 days, which can be compared with the mutual information and transfer entropy from solar wind velocity to JE, which also peaks at tau equals 2 days. But removing the effect of solar wind density doesn't change the peak location, but it lowers the peak and broadens it. So here I just plot the CMIs again for both, just plot these top panels here on the. So we can, previous studies have attributed this effect of the solar wind density to magnetopause shadowing. So I'll use this diagram here to explain what that means. An increase in solar wind density would increase the solar wind dynamic pressure, which would compress the magnetosphere, make it smaller, and which causes then some of these electrons in the radiation belts in this red region to intersect the magnetopause because the magnetopause moves in. And then these radiation belt electrons then would escape to the solar wind. That's how the solar wind density can anti-correlate with the radiation belt electrons. Several mechanisms have been proposed to explain the effect of the solar wind velocity on the radiation belts. The most popular one is called the local acceleration mechanism, which is caused by the VLF waves, very low frequency waves during particle injections. So basically, an increase in solar wind velocity would increase the frequencies of the substorms, which would inject particle from the plasma sheet, the orange region, to the inner magnetosphere, to the pink region. And these particles are colder than the population in the pink region. So there is this mixing of hot and cold particles, which would lead to a Whistler mode waves, Whistler mode chorus waves to be precise. And these waves can accelerate the electrons to the MeV energy range. And so what this shows here is that the time scale for the electrons to get accelerated to the MeV range is about 2 to 3 days. All right, so here we can compute the information transfer from various solar wind parameters and magnetospheric parameters to the radiation belt electrons. Solar wind velocity is at the top. It transfers the most information, followed by SIMH, which is an index that is a proxy for the ring currents, and followed by the interplanetary magnetic field magnitude, IMF B, solar wind dynamic pressure, and so on. So we can, using the information, we can build empirical model to predict the radiation belt electrons. So this slide here gives an overview of this project that is still ongoing. So we use information theory to identify relevant input parameters and response lag times, and then we input these parameters to a neural network and predict the radiation belt electrons. This is still a work in progress. So we can just focus here on the bottom panel. The orange curve here shows the model predictions, and the blue curve shows the observation. So it's the prediction is very good sometimes, but sometimes it's not so good, such as shown right here. So these are just two intervals. But I would like to point out that without the AL and SIMH, AL is a proxy for substorms and SIMH is a proxy for a storm. The model prediction is not as good compared to the model that is built and trained with the AL and SIMH. And so just going back to this table here, using information theory, we find that the SIMH is ranked number 2 and AL is ranked number 5. So without those two parameters, the model doesn't predict radiation belt electrons very well. So it sort of confirms the importance of these parameters as identified by the information theory. All right. So now, is there any questions about radiation belt before we move to Saturn? Okay, so we have sent a few spacecraft to Saturn. The latest one was Cassini. So these spacecrafts regularly observe radio waves originating from the planet. This shows here an example of the radio wave data taken by RPWS instrument on board of Cassini spacecraft. So just to explain this a little bit, the x-axis is time, the y-axis is frequency, and the color is the electric field power spectral densities, which can be obtained from, say, Fourier transform. So just as a reminder, say that we have a sinusoidal function here called S1, a blue curve, and then S2, the green curve, and the red curve is S3. If you combine these signals together, then you get a complicated signal, or that is shown here at the bottom. And one way to analyze this complicated signal here is to break it down to their individual frequencies using Fourier transform, which is done here at the bottom. So you can see here that there's a peak here at T1, which corresponds to the frequency of the signal one, S1 here, and the same peak at the green line here is corresponds to the signal number 2, and the red line corresponds to the signal number 3. So you can break down the complicated signal to their individual frequencies. And so that's what this is. The color here tells you the amplitude of these frequencies. We call it power spectral density. So it's a nice way to analyze a signal. All right, so here it's interesting to play what this signal looks like. Oh, well, maybe I should go back. So the most prominent feature here is what we call SKR, Saturn kilometric radiations. But in addition to SKR, there are smaller features such as these features here, which we call the 5 kilohertz narrow bands. And then there is the 10 kilohertz narrow band, and then 20 to 30 kilohertz narrow bands. And many of these features are periodic. You can see, for example, the 5 kilohertz intensifies and periodically, like about every 10, 11 hours or so. And it's not clear what causes this periodic intensification of these radio waves, these 5 kilohertz narrow bands. So it's often interesting to play what this narrow band, 5 kilohertz narrow band, would sound like if you convert that to a radio, to audible signals. This is the 5 kilohertz sound. And it's so it's very monotonic because it's 5 kilohertz, which is right around here. So what is more interesting here is the SKR, which I showed earlier, to be the most prominent feature in the radio wave data. And this is not what we analyzed in this study, but I'm just playing this because it sounds more interesting than the 5 kilohertz. It sounds a little bit eerie, and you can hear the frequency as is being played to the audio signal. So now you can hear a lowering of the frequency, and then now you can see an increase in frequency. And all right, so it's kind of interesting. Well, Cassini spacecraft also carry an instrument called INCA, ion and neutral camera, which could image the energetic neutral atoms, ENAs. So ENA in space is created when energetic ion charge exchange with a neutral atom, and then now this energetic ion becomes neutral and can travel along a straight path to the camera. And so this is how the ENA instrument works. So this shows here an example of a movie of ENA images. So we can see that there is this periodic intensification of a blob, ENA blobs. They after intensifying would co-rotate the planet. So the Saturn here is at the center of this circle. So now you can see there's an enhancement, and then it will rotate against with the planet. So Saturn rotates on its axis. So this blobs also rotates along the rotate around the planet, and so this ENA intensification has been associated with particle injections at Saturn. So this is an MHD simulation on the left of the particle injections at Saturn. And the right here is a simulation of the resulting ENA emissions. So you can see that there is this periodicity of the intensification of the ENA emissions at Saturn. All right, so morphologically, there are two types of ENA injections. The type 1 usually is found further away, about 10 to 12 RS. 1 RS is about the radius of Saturn is about 60,000 kilometers. And it's wider and more intense, and it's believed to be caused by a reconnection or current sheet collapse. Type 2, on the other hand, is narrower in the local time, and it's less intense, and it is believed to be caused by interchange instability. So in this study, we focus on type 2 injections. So it's difficult to work with these 2D images. So what we have done is that we create what we call a kilogram. We take a slice of this image at particular local time. So in this case, it's from 21 to 3 magnetic local time. Then we get this kind of image. And then we can integrate along the vertical line at certain radial distance from 5 to 9 to get this time series plot. And then we can also integrate the PSD from, say, 3.9 to 6.3 to get this 5 kilohertz narrowband time series. So now we have 2 time series, and we know what to do with it. We can put them on top of each other. We can calculate the power spectral density using Fourier transform, but in this case, I use Lom's-Cargill, which is more robust to obtain the periodicity. And we can calculate the time-shifted cross-correlation, such as down here at the on panel D. The blue curve here shows the correlation of ENA of T with narrow band of T plus tau, and the red curve shows the correlation of the ENA of T plus tau with narrow band of T. So it shows at a peak, the blue curve peaks at about 90 to 120 minutes. The blue curve is more, is consistent with a scenario in which ENA injection would cause narrowband emissions. So this is for one event, and we can look at another event. The peak seems to be different in this event. The peak here is about several minutes, maybe 10 minutes or so. So we gather more events, and then we can compute the ensemble cross correlation of these ensemble events. So I think we have about 8 events here, and but if the processes linking ENA emission to narrowband emissions are nonlinear, then the cross correlation will not be adequate. So on the right here, I show the mutual information of ENA to narrowband in blue and narrowband to ENA in red. And you can see there's a difference. The blue curve on the right here is peaks at about 60 to 90 minutes, or 60 to about 220 minutes, and it has a broad peak, which is not seen in the correlational analysis. And I think this reflects more the variability seen in the individual events. So what we think here is that there is an injection coming from the plasma sheet to the inner magnetosphere that brings hot plasma to the colder environment, which leads to a temperature anisotropy, which then leads to the growth of the electrostatic upper hybrid waves. And these waves, when encountering a sharp density gradient at the Enceladus density torus, which is right around here, they would mode convert to Z mode and then to O mode. And the 5 kilohertz narrowband propagates in O mode. This Enceladus density torus is created because there is a moon near Saturn called Enceladus, and that constantly spews out the coal gases. All right, so we have also sent spacecraft to Jupiter, and the spacecraft there also observed periodic narrowband radio wave emissions, and it's not clear what causes these narrowband emissions, but we think that it's the same process. Similarly, astronomers regularly observe periodic radio waves originating from distant objects like brown dwarfs. Again, it's not clear what causes these radio emissions, but we think that the same process might occur there. And we also expect that some exoplanets would also emit periodic radio wave. All right, so I don't know what time it is, but maybe I don't have time to go into sunspot. So I'll just go to summary. We apply information theory to solar wind and radiation belt systems, to solar dynamo, but I did not have time to show it, and to radio waves at Saturn. Information theory can be a useful tool for input and output problems. It can establish linear and nonlinear correlations, untangle the effects of input parameters that are correlated or anti-correlated with one another. And information theory can be useful for modeling, select and rank input parameters, determine prediction horizons, and detect changes in the underlying dynamics of the systems. I didn't have time to go over these last 2 points, but I did show how we can use information theory to select and rank input parameters which is useful to develop the predictive modeling. All right, so that's my talk. Thank you very much, and I will entertain any questions.
Well, what was okay? I had a I had a question a little bit earlier when you were talking about the Earth's auroras.
Yeah.
I was wondering if are the auroras always centered around the Earth's magnetic poles?
Oh, so to the first order, yes, but this there is this. Let me. I can bring up the figure again. So the answer is yes, but the location changes.
Right.
So okay, so this is what aurora actually looks like if you can see it from space. The night side is right here, which is the most intense because the acceleration, like substorm acceleration, occurs on the night side.
Right.
But so it looks like, typically it looks like an oval, and the pole will be right at the center of this oval. But depending on the magnetic activity, this oval can contract or expand, in radius, and so the location may change. So I think in the lower 48 states, it's very rare to see aurora, except during a very large magnetic storms. Occasionally we have events like those, and then in those events, this oval will expand equatorward to reach say the upper states of the U.S. But I think one time it can reach as far south as Florida. So yeah, the location can change.
Okay. Thanks.
Would you load up mine?
I have a little bit of a follow-up question, I
Yeah, sure.
guess. When looking at the image just now, so the night side is brightest because that's where all this stuff is coming from, right?
Yeah.
So
that's right, because I talk about substorms and in storms, they occur on the night side, and they energize these processes energized, or these phenomena or processes energize the electrons and ions, and that's why it's brightest on the night side. But another reason why it's brightest, if you from the ground, on the day side, the aurora is more difficult to see because of the interference with the sunlight, right, on the day side.
right.
So that's why people often see aurora on the night side only.
The question I was going to ask is, I noticed that like there's in the picture, the bottom side is brighter than the top. So I was wondering if there's a difference between if the aurora favors dawn versus dusk differently at all.
Yeah. So there is the dawn-dusk asymmetry. So I think you're talking about this picture still, right? I would think
Yes.
that this region here is probably pre-midnight, like about 22 MLT. That's where the substorm usually occurs. And so this region here, that is probably post midnight or dawn right here. So usually it's brightest from dusk to midnight. There's another reason for that, besides the substorms that I meant and that occur on the night side. The field line currents from dusk to midnight is upward, which means the electrons come down from the magnetosphere, and frequently there are field line potential drop associated with these upward field line currents, and so this potential drop accelerates these electrons downward, which can make it very very intense aurora. So I think so usually it's dusk to midnight that is where you can see the brightest aurora.
There are a couple of questions coming up in chat. One of the questions is, do you know the atomic transitions that cause the colors?
Yeah, so usually I think it's the hydrogen and nitrogen lines. I think it's the let's see, I don't remember specifically which ones, but the Lyman alpha, I think, is one of them. I studied this a long time ago. Maybe Jay remembers.
Yeah, so the green color is an oxygen line, and the reddish color, if it's at high altitude, it's an oxygen line, and if it's at low altitude, it's a nitrogen line.
Thank you. Another question from the chat. Is there a warning system to anticipate sunstorms or anticipate aurora?
Can you repeat it again? Is there what?
A warning system?
Oh, yes. Not very good one, I would say. However, NOAA website, NOAA has a unit called SWPC, Space Weather Prediction Center. You can Google that, NOAA SWPC, SWPC. And they do have websites that give you a nowcast of aurora and also nowcast of geomagnetic activity indices like KP, CMH, but the accuracy would say that it varies, depending on the conditions, solar wind conditions. I would say that we are not at the same level as terrestrial weather predictions, but I think for many space weather users, those predictions are still very useful. Like satellite operators use this prediction to turn off some instruments on board of satellites, or to put, or to set the instruments on board of satellites to a safe mode.
Thank you very much.
Yeah,
another question came up in chat. How do you know what tau values to check when calculating the time-shifted correlation?
How do I know how to shift?
What tau values to check?
Oh yeah, we just do a whole range of tau. We just pick from tau equals 0 all the way to depending on the problems, like for the radiation belt, I think we carry it out to as far as 1 week or 10 days. We can see that the curve will start will start decreasing to the noise level, and we carry out we can keep increasing the tau, but there's no change. The mutual information, conditional mutual information, the transfer entropy will hit the noise level and will remain there for a long time. So that's when we stop. But I think that most studies would probably not go further than 10 days for the radiation belt response. But I think I have actually I take it back. I carry it out all the way to 1 month, and there is no let me go back there. Yeah. So here's an example. This is the solar wind density. So we can see that the solar wind density mutual information or transfer entropy peak at tau equals 1 day, and then it drops to the noise level at about 5 days, and it remains there all the way to 40 days. So most studies stop, right around 5 days or 10 days.
Are there any other questions?
Maybe Simon can make a few comments about what sort of preparation a student might want to have if they were to go into this field, what sort of career paths, what sort of job opportunities.
Yeah, I think so. For the preparations, I think an undergraduate degree in physics will be useful, and also some training and classes in computer programming will be quite useful, because a lot of times for observers like myself, we spend a lot of time on the computer, sitting in front of the terminal, just analyzing data by writing computer code. And so some statistics will be also useful for that. And then we go to graduate school, where we will take more classes. The classes that are useful here will be electricity and magnetism. Of course, waves will be useful, and I guess maybe mechanics will also be useful, and then so in graduate school you will be connected to a thesis advisor who will direct you to work on a specific topic that usually involves downloading data from a data repository site. So in space physics, NASA, which is the main organization that funds a lot of the space missions, NASA is very good at requiring the instruments PI to put their data publicly available online at this at data repository sites. There are several of those, and then so the project would typically involve downloading this data and then write computer codes like MATLAB, Python, Fortran-C, whatever your favorite language might be, and analyze them. I've shown here that you can use information theory, but you can use Fourier transform, correlations. You can use a standard correlation analysis to look at the data and plotting the data, plotting the images. And then, so after you get your PhD, you can work as a postdoc in the academic institutions. But some people, so if you do that, then you are committed to doing research again, and then hopefully you will advance from postdoc to a permanent position, or maybe professors at the academic institutions. But that's not the only path. You can get a position in the industry or in the government labs. Like you can work at the NOAA SWIPC, which employs many PhDs to help with their operation there, to provide the space weather products to the public, to the nation. You can work at NASA to help support the satellite instruments. And besides those, you can also work at industries, like I think companies like Lockheed Martin, Boeing, I think also employ many space physicists to do whatever they do. I think many PhDs also work for oil companies, so their jobs include analyzing space images of the Earth, looking for a new oil field. So there's a wide variety, and of course, many PhDs with space physics are very good with computers. So many of them also end up working for companies like Google's, Microsoft, Facebook, and so on. So there's a lot of opportunities.
Well, thank you very much, Dr. Wing.
Thank you.
If anyone wants to stick around, you're more than welcome to stick around and ask Dr. Wing any specific questions that you didn't want to ask in front of everyone. But otherwise, we're going to go ahead and close this up. Thank you all for being here. Are there any final questions? Okay. Thank you very much for being here, Dr. Wing.
Yeah, thank you very much for having me. It's been a pleasure.